Good afternoon, everyone. My name is Nancy Badu, and I'm an Associate Director here at the Steel Construction Institute. A very warm welcome to today's webinar. In fact, this is the last webinar of 2025. Last but not least, by any means, you are in for a treat. We've got a presentation on structural steel castings by Jennifer Pazdon, who is the director of the UK division of the company CastConnex.
Thanks very much, Nancy. Hopefully everyone can hear me okay.
Yes, we can.
Great. Okay. Thank you for the introduction. Thank you everyone for coming today to this last SCI webinar of the year. It's quite exciting. I am looking forward to 2026. So today's presentation, as you know, is structural steel castings, focusing on publication P441, which is the publication by the Steel Construction Institute that we at CastConnex had the pleasure of supporting along with other experts in the field in the review process. Before I get into the section on P441, I just wanted to take this opportunity to quickly introduce CastConnex. We are structural engineers who design and supply cast steel connections for buildings, bridges, and other structures. Throughout the world, we have put castings into tens of thousands of structures in North America and globally, both building and bridge projects. We have offices throughout North America, and in 2023, I relocated to London to establish our office here. A lot of the work that we do is what you will see explained in the presentation. Part of the role of the casting designer supplier is this concept that we are assisting structural engineers, architects, steelwork contractors, and other construction professionals to understand how a steel casting can be leveraged in their projects. That often means doing a lot of support sort of at our own risk or for free at the beginning, so that we can help folks that may not be accustomed to using castings in their projects understand when they are applicable, understand all of the implications of value that the casting is offering as an alternative to conventional methods of fabrication. In the presentation, we will talk a bit about standardized and custom products. CastConnex offers both. And so on to the meat of the presentation. So we'll be introducing publication P441. It was officially out and available on the SCI website. It's also available on our website earlier this year. And we'll do an overview of the contents. It's a very dense resource. There's a huge amount of information, although I've read every word of it several times, just revisiting it to put together the slides for this presentation. I again pick up on things that I had sort of forgotten that were in there. So it is absolutely the ultimate resource for castings and construction. We will look at some of the case studies to sort of reflect the contents of the guide. And along the way, we'll be looking at frequently asked questions. So what are some of the ways that we can think about the content that is in this guide? How do these manifest into real world questions? And what are some of the ways of answering those or thinking through them? So as I mentioned, published in 2024, really available earlier this year, authored by Nancy Badu. And Nancy also authored a SCI publication P172, which was published in the 90s, called Castings and Construction. So in some way, this is P441 is an update, but also an expansion to bring it to explaining more modern methods and more recent case studies. Comments were provided by experts in the field of structural engineering and the foundry industry. The publication essentially gives guidance on the properties, specification, and procurement of carbon steel and stainless steel structural castings. The relevant requirements in current European product design and fabrication standards are interpreted. The guide emphasizes that the specification of the appropriate level of quality of the casting is very important and requires close liaison between the foundry and the design and construction team, or we'll see how the casting designer supplier also sits in sort of straddling over the foundry design and construction team, and then also includes these case studies. So the table of contents you can see on your screen. As mentioned before, we will not have time to go through each of these with a fine-tooth comb, but to give you a sense, we'll start with sort of introduction, procurement, and properties, and then I will make an attempt to address what is in sections 4, 5, 6, and part of the Appendix B with a case study But certainly very good idea to go back and read your free copy from the PSI from the SCI to get a closer look at these. Many of the images that you'll see in this presentation are actually included in the SCI guide to give a nice example of representatives of castings that have been used in construction, as well as their design and specification. So to begin with the introduction, part one, we look at why to use steel castings in construction. What is a casting? Examples of structural steel castings. Rather than kind of go verbatim word for word in what the guide says, I will give you my own sort of impression about, from my experience, why we use castings in construction. And then you can find that in further detail and in Nancy's words, similar reinforcing and more in-depth comments in the guide. So what are structural steel castings? So anyone on the line who has worked on the design of a steel building is familiar with wrought steel, right? So wrought steel, as a matter of fact, is first cast. So what you're seeing on your screen right now is a continuous casting process where molten metal is poured into a die. It's then extruded to create either the plate, angle, wide flange shapes that we are accustomed to using when we are setting about to design and to construct conventional steel buildings. These extrusions are sensible and vital and absolutely do not have an adequate replacement when it comes to members such as beams and columns. So when we're looking at castings, we're looking at joints essentially, but we don't want to be thinking about replacing a wide flange with a cast beam. It would not be as efficient of manufacturing process. So there's a very good reason why we have wrought steel. I like to lead with that because I will be using a lot of comparisons to where, when we're looking at joints, wrought steel, because of the inherent mechanical properties, may be inferior to a cast steel solution, but it's not to say that wrought steel in general is inferior to casting. Those material properties come from the manufacturing process. So we're rolling the steel out, we're flattening and aligning the grain patterns, which means that the steel is actually not isotropic. But our codes address this, right? We know that we're not meant to load a plate perpendicular to the direction of rolling for the risk of tearing. And our codified equations are taking into account residual stresses and things that exist in these standardized manufactured products. The difference with a casting is that we are creating a mold, we are pouring molten metal into it, and it solidifies in that mold. So the finished geometry of that joint is that of the mold, so rather than an extrusion. What this means is that we have virtually limitless opportunities for optimization of material usage, so to put the material where we need it for the flow of forces through the joint. It also means during the manufacturing process, it's tightly controlled so that we have what's called directional solidification of the element, which means we preclude that centerline strength that can happen in wrought steel. And so we actually have high quality isotropic material through this joint, which is located at a connection where we have the highest forces and triaxial stress states to be considering. From an architectural standpoint, it's quite exciting because we're able to sculpt structural steel. So we can be exposing our connections rather than being, you know, as a structural engineer, many people never see our work. Although we know it's there because everyone is able to use the building or structure safely. But to be able to expose the structure is a nice asset that castings offer as well. So the first use of structural steel or castings in steel structures was not at all architectural, although you can see that this cast steel node on the left is kind of lovely. It does look rather sculptural. Its use is purely driven by structural performance. So it will live in will be an offshore wind turbine tower. So you can see in the inset there, this tower is a mock-up onshore, but eventually it will spend its lifetime halfway up its neck underwater, constantly battened by wind and wave action. And so that's where we're seeing these considerations for fatigue arising. And that's really what drove the offshore industry to move to castings, was to simplify complex fabrication and vastly improve fatigue performance of these connections in an extremely arduous loading condition and an extremely corrosive environment. So if we start from that platform of understanding that castings are applicable for these massive structures with these arduous loads and corrosion concerns, we can see that we're covered quite a bit for the levels of loading and whatnot that we would see in onshore structures. So for sense of scale, those are very large boats in the forefront there. So this is a massive, massive truss structure. Again, will live its life underwater. If we start to think about what was done from a conventional fabrication standpoint before they turned to castings, if we focus on one of these multi-planar, multi-tubular connections and think about what would be in the sort of toolkit for conventional fabrication, if we if you imagine that all of those elements were to equally have equal hierarchy and intersect each other in sort of a bird's mouth cut, if you did sort of a Boolean subtraction with equal hierarchy, you would end up with all these sort of bird's mouth and parabolic cuts. These joints are extremely challenging to design. They're extremely challenging to fabricate. So even if you can design something, doesn't mean that it can be built, which is an important thing to remember as we get into more complex geometries and ambitious structures. So that type of profile cutting of pipe or tube and fitting is very challenging, time consuming. And then the quality of the weld that can be laid down is a challenge because the weld access is difficult. The length of weld is significant. If you have welds overlapping welds, these are all things that are going to lead to poor fatigue performance as well as just general in-service performance potentially. So to address those sort of weld-toe overlaps and complex cuts, you can envision one of these members as a through member, upsize its outer diameter so the intersection with the other members is pulled back. You still have profile cutting parabolic cuts, but you're avoiding that weld-toe overlap. But we've also just increased the tonnage of the structure just to address that local issue at the connection by increasing that inner diameter. Also, because of these tubular sections, the connection points can be quite soft. There is a need for some sort of internal stiffening. So often this would be done with welded steel plates inside of the connection point. So more labor, more tonnage, more expense, and still the lifetime of these connections, they were sometimes seeing failures after about 10 years using conventional fabrication. So driving this idea of return on investment, the offshore industry, I think we can say is we really owe it to them that we're able to now use castings in construction because they spent a lot of time in research and development and also using modern methods of computation to be able to structurally analyze steel castings and also run simulations to be able to understand the manufacturing process and the quality that we would get using different processes. There are standards in EN and ASTM that define the methods for making a casting, the processes for manufacturing, the qualifications of personnel, the inspection and whatnot, which we'll touch on briefly. And those are all relevant to the construction industry, but they first kind of came to their fruition in offshore. So we can see in the cross section here that we're putting the material where we need it for the flow of forces through the joint, thinning out to match the member wall thickness away from the joint. It was not very long until clever engineers recognized that castings could be leveraged onshore, and many of the first examples were in bridge structures. So here you see some pedestrian, rail, vehicular bridges utilizing cast steel joints at their truss tubular connections, at these trees in the pedestrian bridge, and at the base of this arched rail bridge that you see in the top right. The considerations for fatigue are also a concern in bridge construction. Some of these are signature bridges that are quite lovely. So the ability to have these attractive exposed connections is sort of first most evident in bridge construction where the structure is the architecture. And then further along, we start to see examples in building applications. So in tensile structures, Munich Olympic Stadium has these massive castings that are addressing these multiplanar tensile connections. Centre Pompidou, the exterior exoskeleton of the structure utilizes these massive castings that they are called Gerberettes that are supporting that tensioned exostructure. And then closer to many of you on the call here, I'm based in London. We have Paddington Station, these cast steel trees and tapered ends, column ends and branch ends. If you've been to Terminal 5 Heathrow, you cannot miss the castings on the floor right in front of you. And then, of course, King's Cross as well, which is featured as a case study in P441 itself. So why do we want to use steel castings in construction? What was driving the use of it now that we've seen some examples of what a steel casting is? This is described slightly differently in the guide, but again, for some variety and different perspective, I'm headlining these sort of benefits slightly differently. So material optimization, enhanced strength and stiffness, improved fatigue life, simplified fabrication, improved constructability, and aesthetics. Speaking of material optimization is the idea that we can sculpt structural steel, right? So we can create a mold that has geometries that would be impossible to achieve with conventional fabrication that allows us to place the material where it's needed for the flow of forces through the joint. And another way of thinking that is to remove material where it's not needed, right? So that we're able to lighten the tonnage and we're able to have more efficient performing structures and reducing carbon, embodied carbon as well. Enhancing strength and stiffness. So when properly manufactured, cast steel can achieve isotropic material properties, which is ideal for these connection points where we have complex stress states. And local limit states that would typically control conventional connection design are limited. We can also just better understand the stiffness of a casting very early in the design, which can then be incorporated into your global model to help to lighten the overall structure, particularly for structures sensitive to natural periods. Improving fatigue life. So weld access is improved, fatigue performance is improved by moving welds to locations of lower stress. Service life is improved as compared to conventional fabrication. In general, we're simplifying fabrication. So we're replacing complex weldments, simplifying cutting, fitting, and welding activities that would happen in the shop or in the field, trying to, as much as possible, simplify and have no welding happening in the field. And then another consideration is if there is a requirement for weld remediation, the fewer welds that you have, the less there is to remediate. And so the casting is replacing those weldments with one monolithic piece of isotropic steel. Improving constructability. So every standardized product that we have developed and every custom product that we develop, we're thinking about through the whole life cycle of the project. So not just can it withstand, the loads or structural performance requirements, how will this be incorporated into the steelwork contractor's assembly? How will it be assembled on site? And what are the different assets that we can add to the product to assist in constructability? So overall, improving shop and site fit up and reducing overall project delivery timelines, which is again equating to savings and cost. Aesthetics. I don't know how many architects we might have on the line, but if, like me, you are a structural engineer who appreciates the aesthetics of structures, this may resonate. This is actually a quote from that I think our CEO wrote it, so I put it in quotes so that you don't think that I came up with this brilliant saying. But if you could sculpt structural steel, what would you have it do? I think it's a really nice way to think about this. And when speaking with architects, you see their eyes light up with this idea that, we can be part of the structure. It's not that we have to think, we draw a picture, we want it to look like this, and then we have to fight with the structural engineer. It becomes more of a collaboration so that geometries can be realized that are unachievable with conventional fabrication. The structure can become the architectural expression, and in a way that is sensible and efficient from a structural standpoint. When we talk about considerations for exposed steel or AESS, architecturally exposed structural steel, castings are going to greatly reduce the amount of craftsmanship, skill, and labor hours required on the part of the steelwork contractor to achieve high quality AESS. So some examples of structural steel castings. We have sort of two typologies. We have the custom casting, which is project specific, engineered and detailed for specific performance requirements of the project. Later, in a later section, we will look at a case study of a custom project, which is the sphere at the Venetian. And then standardized castings. So these are elements that are pre-engineered. They're available off the shelf. They come in a range of sizes. Economy of scale is achieved in these because they've been standardized and they're produced en masse. So a consideration with a custom casting can be whether or not we have repetition. So the more repetition we have with custom castings, the more we can amortize the upfront cost of engineering and tooling up to make the part. With a standardized casting for any project, public schools, public libraries, civic buildings, as well as museums, stadia, and airports, but the product costs the same, whether you buy 2 or 300. So that is opening up the opportunity to use castings for projects of any size and any budget. Applications, again, as explained before, ideal for AESS, mass timber, seismic applications. It's not a focus of this talk or the guide because of regionality, but there are many, we actually have many cast steel products that are available off the shelf that are meant to be part of seismic force resisting systems. And constructability. So some of the examples that are shared in the guide, we have fork-ended or clevis pin connections, true pins for connecting to hollow CHS or mass timber, a conical or tapered end, which is for, say, an architecturally exposed application. Up at the top there, you see some examples of tie rods or cable connectors that we see quite a bit in London. Some really nice techie architecture. Cannon Place is featured in that image there. And then onto the concept of constructability, this is a product called the Diablo bolted splice that allows for completely field bolted splice that can be concealed and relieves the steelwork contractor of the many hours that would be required in the shop welding just to achieve one field bolted connection. All right, so I thought I would, we'll get to the first FAQ here, which comes up often, which is cost. So some of the things that I hear paraphrasing is, wow, these must be really expensive because they look good, or they're so high quality, they must be expensive. My project can't afford these. The contractor told me that castings are too expensive. So these are things that I used to hear more, but And the way that I would answer these, it's important to appreciate the full value of an engineered cast product. One must look holistically over the life cycle of the project for cost savings and risk reduction. Also consider that it would not be proper to compare the price per ton, say, of an engineered product to the price per ton of steel plate, right? Steel plate is a raw material. It's not been engineered. It's not been shaped. It's not been fabricated. So it's important that we look at these we don't look at them as an apple to oranges comparison, but we really appreciate the value that's offered in the design phase to the steelwork contractor, to the erector in the life cycle of the project. So some things to consider: life cycle cost savings due to overall tonnage reduction. So as mentioned before, if members are designed for member forces, they can be significantly, or they can be as efficient and as lightweight as possible when they are not controlled by local limit states. Reducing shop and field time by simplification of the complexity and reduction in labor hours. Increasing coating system longevity, so for bridges or other exposed structures, because castings have these very gentle radii and easy to access welds, they will have coating systems that last longer. That's not something that we always think about in the buildings world, which is where I come from, but it's a vast expense over the lifetime of a structure when we talk about a bridge or something exposed. And then improving fatigue performance, of course. So if we can get more cycles, we can improve the lifetime of the structure. And then also think about leveraging the fact that we can achieve enhanced strength and stiffness with castings. So we can much better understand the stiffness and the strength of the connection because we've modeled it in 3 dimensions, right? So it's something that can be much more closely predicted, say, than what one might assume in an analysis model, or what codes might be telling someone to assume for stiffness and conventionally fabricated connections. Repetition and economy of scale through standardization. So I've mentioned this before. So when it comes to cost, we have to remember these standardized products that are available off the shelf and make them accessible for projects of any budget. Also with custom castings, when we have repetition, we can get more economy out of it. So on some projects, people might consider a casting and without understanding the fact that if you have only one, it may not be feasible. If there's no other way to achieve it, it may be feasible. It may be, worth the price point. But you can't just assume that castings are expensive because you need to be sure that you were considering them in the right application. On the design side, these are pre-engineered, or if it's a custom casting, it would be engineered by the casting designer supplier. So that means you as structural engineers, or if the steelwork contractor is responsible for connection design, that is no longer your onus. So you can specify the product. For the standardized products, all of the capacities have already been tabulated. For the custom ones, that would be included in our price again. So that's something to consider with the full value that comes in the price of a custom casting. And for projects that have complex fabrication, or would have complex fabrication, or have architecturally exposed requirements, with a casting, we can skip the mock-up because there's no need to prove out the complex weldment. We've replaced it with one monolithic piece of steel. And for the standardized products, they all look the same. So if you want a product sample, that can be your mock-up, which can have a huge effect on project delivery times, as well as risk and overall cost. Proper specification, also things to consider. This is kind of what I was alluding to before. If you choose the wrong tool for the job, it's not going to look cost competitive. So it's important to understand when a casting is appropriate. So seeing examples of successful projects, and also accessing the guide P441, and then speaking to casting designer suppliers can also help you. And early on in the project, understand the cost implications. So look for ROM budget pricing if it is a custom or if it's a standardized product. Another frequently asked question is about lead times. So we'll see how castings are manufactured in a few moments. And the question I get all the time is, what is the lead time for castings? So there's kind of 2 different ways of answering this, or 2 different answers that are important. For custom castings, we'll see later that this involves engineering, development of shop drawings and engineering report. Then in the manufacturing process, it's development of tooling and the process, proving out the process of how we're going to produce the castings. And then once that process is proven out, the production time, we can sort of churn the castings out rather quickly. But for all of that upfront time, once we have approved shop drawings, we typically say now a good rule of thumb is to say 28 weeks from the time that shop drawings are approved to the first delivery. So that would be the first tranche of casting. So if you have a project with 10,000 castings, we're not going to deliver all 10,000 of them at once. You wouldn't have anywhere to put them and you wouldn't be able to work with them. But we will deliver them in tranches that make sense to fit the project delivery timeline. I would say 28 weeks is a good rule of thumb. Compressed schedules can be arranged. It really just depends on the project needs. So engaging in early discussions with a qualified casting designer supplier will support you in properly specifying performance requirements and geometric information on your contract drawings, so that when the project goes to tender, the information that is needed to develop the casting concept further is there. And then also, we can talk about understanding project-specific lead time. So times when maybe 28 weeks wouldn't quite be a good rule of thumb. For standardized castings, these are available off the shelf. So it's essentially, blasting them, putting them in a crate and shipping them. So we often say something like 8 to 12 weeks, but again, this can be discussed. The thing to consider with this lead time also is that you need to understand that schedule time in construction is recovered with the decreased labor and complexity, tighter tolerances, and consistency of the product that you're receiving. So it's important that when the construction team is looking at the lead time for a casting, they don't double count all of that welding time that they would have done to achieve the product word of fabrication, and also understand that things are going to go together much more tightly in the field. Part 2, procurement of custom castings. So this is where we will introduce or further delve into the concept of the casting designer supplier, and then contrast that against what's in the guide called the traditional procurement option that has been used in the past. So the casting designer supplier scope of work, hopefully this graphic is large enough for you on your screen, but on the graphic on the right, it's adequately large in the guide. You can see in yellow the casting designer supplier, and the solid lines are indicating contractual relationships, and the dotted are the functional or communication relationships. So the casting designer supplier is a subcontractor to the steelwork contractor and encompasses the foundry. So the casting designer supplier is responsible for this sort of pre-tender or complementary design exploration services that I explained before. When under contract with the steelwork contractor, we take full responsibility for design, detailing, and engineering the castings, which is where that functional relationship of coordination with the steelwork contractor, structural engineer, and architect, once we've received the contract. We then develop casting shop drawings and an engineering report, which are submitted to the project for approval and for record. We then oversee the manufacture of the casting. So we work with various different foundries. Different foundries are most capable at different types of castings. So a casting that might be a smaller standardized product, there's some foundries that would be better equipped to produce those versus say these massive castings, that would be a different shop that would do that. So having different subcontractors ourselves helps us to be flexible and cover the range of applications that we see in the construction world. Our communication to the foundry is, you can think of it in a way as translating the structural performance requirements to foundry speak. So there are standards in both EN and ASTM that define casting production, but there is no direct translation from, I need a S460 connector that's a true pin to what a foundry is going to do. So we produce a production specification for the foundry, which along with the shop drawings is the instructions on what they need to produce. It includes all of the NDE requirements and all of the submittals that we would need to be able to sell into the construction market. So we have that traceability and we have that proof of quality. The difference that's outlined in the guide with this idea of a traditional procurement option is that you are lacking one entity that is overseeing coordination among all the parties in design and construction. And so you have the responsibility of engineering might fall with the structural engineer, or it falls with the steelwork contractor. The foundry is not a structural engineer. They're not going to design a casting for you. Who's responsible for full detailing and shop drawing production? The shop drawing process is different from detailing shop drawings that are used in the construction industry. It falls under different standards. And then the production specification and manufacturer, who is actually overseeing that. So it's not something that any of these teams in steelwork industry or structural engineer would have expertise in. And again, for the foundry, they are quite expert at making castings. They do incredible things, but they are not structural engineers, right? And nor do they want to try to take on that role or purview. So this can result, as you would imagine, in scope gaps, project delays, and potentially worst case performance and quality issues with the product itself due to not to lack of capacity on anyone's side, but just due to that gap in understanding and coordination. All right, section 3, properties of cast alloys. So we have a few FAQs. Basically, this whole section is an FAQ, I thought, because this is a very common inquiry that we get. And a lot of the questions that come up about this, I think, are related to the fact that we are more familiar in the industry typically with the term cast iron than we are with cast steel. And so understanding with this a priori knowledge that cast iron is brittle and you can't weld to it and can't take tension, all these things, there's often sort of a misunderstanding at the beginning that what we're talking about steel, we're not talking about iron. So properties of cast alloys, we'll look at some product standards and we'll talk about weldability. BSEN 10340, steel castings for structural uses, is the UK designated standard for steel castings. So castings supplied to this standard are able to be CE marked for use in the construction products industry. And the UK National Annex to the second generation BSEN 1993-11 will reference BSEN 10340 as well as this guide. So other than that, there isn't a specific product standard, which is sensible because custom castings are custom, right? They're bespoke. They're have requirements that are project specific. So to create one product standard for custom castings would be a fool's errand. And that's why neither Eurocodes nor the AISC specifications or CSA have these. Just to let you know, there is an equivalent ASTM 8958 for those that might be designing from from Europe or wherever you're located, but working on projects perhaps in the Middle East or other locations that would be using AISC specification and ASTM standards. So some FAQs about properties of cast steel grades. So a question that I receive or used to receive more, but hopefully the education is getting out there is, are castings weldable? Are castings brittle? So I intentionally wrote that as castings rather than steel castings. Some castings are not weldable. Some castings are brittle. Some castings are cast of aluminum. Some castings could be cast in concrete. But when we're talking about steel castings, we need to make sure that we understand that we're using steel, right? So cast steel alloys are available with similar weldability, strength, and ductility to standard wrought steel grades. So in this region, speaking of S355, S460, and there are cast steel grades with corrosion resistance similar to stainless grades such as super duplex, and other austenitic. So there are also cast steel grades with mechanical properties equivalent to HSS or high strength steel. So for example, the S690, and some of these are elucidated further. And 10340 is given a tighter analysis in the guide itself. Something to consider, this is, I don't know if this is an FAQ, but this is something that we recognize, and that for our customers, the steelwork contractor, we like to bring this up with them early so that they can be able to anticipate. Many of the cast steel grades that are suitable for construction applications may sit in group 3. So in ISO 15608, group 3 may not be the most common steel in your shop. And so you may need to qualify a PWPS using a cast steel test plate. And so when we offer you our quotation, we include those for you. So there really isn't anything special. There's nothing special about the processes. There's nothing special about we try to use the simplest positions as possible. And there's really nothing special about the filler metals. It's just that the metal falls into type 3 and you may not have worked with that. So you may not have a WPS that has qualified that yet. All right, so sections 4, 5, 6, which are casting design and specification, foundry quality control, inspection and testing, and sustainability, as well as Appendix B on casting manufacturing. I think I will cover that with a case study. There's a huge amount of great information in the guide, but we'll have sort of an example that shows you all of them working together in this next section. And to do that, we will look at one of the case studies that is in the guide. It was called MSG Sphere Las Vegas. It's more commonly called Sphere at the Venetian these days, but it lets you know that it is located in Las Vegas. So this is the largest spherical structure in the world. It's sort of it's a grid shell that is a modified sort of Buckminster Fuller ball. So it's not quite a buckyball. It is 568-foot diameter, and it's wrapped with this massive LED screen on the outside. It houses inside a state-of-the-art performance venue with this really interesting structure that they call the immersive surface or media plane. Again, the highest resolution LED screen sits inside of that hung grid shell, which was an extreme challenge. It would be really fun to talk about, but there's a super tight NDA on it. So there are over 400 custom castings of about 30 family types that made that hung grid shell possible to be within tolerances of millimeters to enable the projection of 3D without glasses and let the speakers hit your ears in the right way so that you have this full immersive experience. This building is really like a machine. So if the bones don't work, or if your chassis doesn't work in a car, the car isn't going to work. And it's kind of the same concept in this sphere. But we'll look at the exosphere nodes. So that red level that you see there. Again, I mentioned it's a modified buckyball because working with a structural engineer of record, we did a parametric study to show that the best way to tackle this project was actually to find node repetition at each one of the latitudes of the structure. So in a buckyball, you don't have node repetition. You do have member length repetition, and for the most part, the members are of similar size, but optimizing the idea of repetition at the castings and the connections made it possible to build this massive structure and make sure that it all fit up together in a timeline that was reasonable for construction. So we'll take a look at this node on the left, latitude 3. When we are in early stages of a project, we will do this complementary design exploration or sort of feasibility studies to take a look at what the cast node option would be, the value that it would be adding as opposed to what might have been a conventional solution. So in this application, you can see the cast node and a fabricated node alternative on the right. Those are drawn at scale, so they're represented at scale. So first you can appreciate that the fabricated node is much more rangy. You can also see in the first line there that it is about 4 times the tonnage. So right there, we can kind of intuit that there would be a huge savings happening here if it's 4 times the tonnage. And then looking at the complexity of that fabricated node, in this grid shell, all of the members are straight. So the curvature, all that geometry, all that control is contained within the casting itself. To try and do that with a fabricated node is very problematic. This thing is massive. That would be taller than me, actually, with my arms out. It would be bigger than me. And you have these 3-inch thick plates that need to be miter cut at a slight angle and then welded. Plate is never flat when it arrives to you. It's hard to flatten it out, and it is going to distort a lot when you are welding it. And so those plates were meant to be gently canted in, precise to like the degree or half a degree. Challenging, if not impossible, to do that, and especially so many times where you're going to have, again, variation in plate quality and things like that. With a casting, you'll see this controlled process, and you'll note in the image there that we're indicating the ends or the touch points as red. Those are precision machines, so they are exactly in the right place when they mate with the incoming flange plate on the members that span between the nodes. The casting itself will see all these other controlled methods so that we know this is really in the right place. A very big concern in something like this, if at one end of the central lat, once we go around, if we were off by, say, half a degree on one side, by the time we get around the circumference of the sphere, we would find that we were off by 27 feet or 9 meters. That's a huge tolerance stack that can occur. And so the only way to achieve a project like this and to for anyone to take on the risk associated with such a massive project, the castings really drive the whole element. And when you consider, of course, the cost of structure as compared to the cost of the entire project, it's important to invest in the structure and spend the time and understanding that it's going to make the rest of the machine possible. So this is where we set about with the information transfer. So the structural engineer of record provided us with geometry, so just essentially connectivity and member sizes. We then build out what you see there, the geometry of the cast component. So we are considering both the flow of forces through the joint as well as manufacturing considerations as we're developing the cast steel joint. Where also you can see the extents of the casting here are driven by that we have these flange plate bolted connections, so we need to be able to fit enough bolts, which is again a coordination process that we went through with the engineer of record. They then supply us with loads, and we load our analysis model with those loads that are supplied by the engineer All of this process, all of the information transfer is all recorded and submitted in the engineering report. So it's clear, which information we're referencing, what were our assumptions in design, what was the process that we set about in the finite element analysis, what were the mesh densities, how are we interpreting the results, and then this is all, of course, displayed in the post-processing, again, all submitted in this case to a peer reviewer, not just the engineer of record. So for analysis, it's interesting. So we're looking at these sort of interesting geometries that don't follow beam theory. So we need to be using design assisted by finite element analysis. But in locations where we don't, we absolutely will follow codified equations. So in this case, this project was under AISC. So we used AISC 360 specifications to design these bolted connections, but also keeping in mind moments where perhaps the codified equations would not be conservative. So the equation for prying, the way that it's developed in the American codes, would not actually address the situation that we have here. It's considering sort of like more of a through plate happening on the end of that casting. And so this type of solid modeling and close analysis that we're able to do, because it's the only thing that we do on the project, right? You would not model a full building as with finite element analysis, right? That's why we have beam elements and columns and things like that to make it reasonable to do frame analysis. But for these connection points, we want to be looking very closely at things. So here you can see we're using a nonlinear analysis to look at the prying and the contact elements to help us know when that is actually becoming separated, to make sure that we have enough meat there basically to resist the prying action. So once we're satisfied with the engineering, we're developing shop drawings, both as cast and machined, which you'll see the reason for momentarily. And throughout that process, we have been considering the in situ or in service application for the casting, but we are also considering, is it manufacturable? So that's another pitfall that can happen for folks. You could draw something that might work from a structural standpoint, but whether or not it's castable is a different consideration. So what you're seeing in this video is a casting, not the sphere casting, but one that supports columns that support a very long span performance venue roof. I'll play this video again just so I can speak while I'm talking you through it. So the gray material that you're seeing is sand, so that the castings are cast against sand in the process that we use. The tan or brown material, that's the core. It's also sand, but that is defining the interior surface of this hollow casting, whereas the gray is defining the exterior surface. You can see the casting or the part on the left, and you can see that there are these other colored parts that are in that void are not part of the usable part. Those are part of the manufacturing process. And we'll see the reason for those elements in the next slide. So back to the sphere casting. If we look at this video on the left, what we're seeing is a CFD simulation of feeding the part. So the white elements that you see, that's called gating. So the molten metal is poured in through the gating, and then we fill the part against gravity. We're simulating it because we need to understand how quickly we need to fill the part and how many gates we might need, so that you can fill the part fast enough so that you don't have the risk of steel solidifying within the gates, but also not so quickly so that we would have so that we would lose lamellar flow. So we want to maintain lamellar flow, because if we get turbulent flow, basically conceptually you're engaging, or you're including sort of like air bubbles inside of the part. So these gaseous inclusions can affect the quality of the part itself. So we're doing this in a controlled fashion through using the modern methods of simulation, and then that goes into the field. And this is something that the foundry actually runs these simulations, but we are speaking with them about, where do we need the best quality in the piece? Where do we want to put these sacrificial risers, which I'll explain momentarily? Where are we concerned about, points where we have the highest stresses, where we need really the highest quality? So we will have a back and forth in coordination with them about how the gating, feeding, and other appurtenances are developed. In this next slide, what we're seeing is rate of solidification or shrinkage. So when a piece of the part goes gray, that means that it has solidified. And you'll see that the last pieces to turn gray are these cylinders that are up at the top. So these are called sacrificial risers. What that means, if we watch it again, is that the metal is solidifying or freezing from one side to the other. So that directional solidification means that we do not have centerline shrinkage. So the shrinkage gap will be inside of these sacrificial risers, like a fist-sized hole, which would mean that the part could tear apart, but it's not part of the usable part of the casting, right? So they're called sacrificial because they are they're cut off and they're recycled and reused in the next batch of production. The tooling to create the sand mold is essentially kind of like a timber version of what will be the finished part. So we use this tooling to create the sort of negative and positive of what will be the finished piece. It's CNC milled from timber for precision. And then if you can kind of imagine on the left, they're filling those CNC milled formwork with sand to create the exterior and interior surface of what will be the cast part. The sand is a specially sieved sand that's treated with a chemical binder. It will set up in a few minutes once it's been poured out. It stays intact when molten metal is poured against it. It is also recycled and reused after the process. So here we can see some completed, I think these are the cope and the drag mold, so defining the top and the bottom surfaces of the casting. There will also be a core that sits inside of lat 3. And then the whole thing is encased in a steel flask to resist fluid pressure when the molten metal starts to be fed into the piece. Someone stands, as I always say, far too close to molten metal for my comfort. But part of that reason is that in real time, they are beginning the process of testing. So there will be ladle samples taken that are mass spectroscopy is run on them to make sure that the alloy is correct. And another FAQ that comes up. So we've just seen the part of the process of casting manufacturing. One thing that I didn't show, but that's important to note, is that steel castings are produced using electric arc furnace. So often, particularly in this region, it's great to hear structural engineers thinking about embodied carbon in projects and life cycle assessment. And so I'll be asked, how does the carbon intensity of cast steel compare to wrought steel? And are EPDs available for steel castings? So there were not EPDs for structural steel castings in the construction world. And so we have developed EPDs that would be applicable both in North America and in European markets. Those are available on the Smart EPD website. And it turns out the carbon intensity of the cast steel material is not dissimilar from wrought steel produced using EAF. So wrought steel produced using BOF there would be a difference there. But the way I like to think about it is not so much trying to compare, it's improper to compare carbon intensity of a material. What we really need to look at is the embodied carbon that comes. Embodied carbon savings can be achieved with cast steel connections because, as explained before, we're leveraging this ability to optimize material usage. So optimizing material for the flow of forces through the joint, and important to consider that we can overall reduce tonnage, right? So that wrought steel can also get a lot lighter because we're addressing local connection limit states and allowing the members to be sized for member forces rather than controlled by connection limit states. All right, so once that part has been poured, it sits for probably about a week. It's solidifying and cooling, which is again controlled and specified in EN 10340, the sort of rate of cooling. The sand, as you can see, the binder has decayed in it, so it will start to fall away from the part. There's a lot of work to be done to kind of push the sand out. And then there will be grinding processes and whatnot to remove those appurtenances, which will be recycled and melted down again, and then to get the part to look how we want it to look. Quenching and tempering, so that many of the cast steel grades appropriate for construction will have a QT process. Part of the NDE that goes on is, you can see I pointed out in this image that we have a keel block that is attached to the casting. So that was produced, heat treated, quenched and tempered along with the casting itself, so that when it's tested, it can be a representative of the casting itself. However, we also have a whole suite of non-destructive examination that is performed on the production part itself. So the common types of testing are RT, UT, MT, visual, sometimes others, depending on which market you're working in. And the idea is that no piece of material is actually perfect, right? And it doesn't need to be. So it's understanding what is an acceptable flaw, and then setting that criteria for the inspectors that are working on the part. So we can have allowable indication sizes and allowable distribution, depending on how close they are to each other. They could be more or less detrimental. And so we will set those requirements in our production specification, referencing the applicable standards. Areas of the casting that have indications that exceed the acceptance criteria are, it's sometimes called weld repair, but it's really best to think about it as production welding, because it is anticipated that there will be some process of arc gouging out and replacing areas that exceed indications. They're then re-examined to confirm conformance to the original parent material specification, and then there's a final heat treatment to relieve residual stresses. So I thought I'd revisit this again. So an FAQ is, are there requirements for NDE or NDT for steel castings in Eurocodes? And isn't it the best practice to select the most stringent NDE protocol? Neither BSEN 15592, which is founding technical conditions of delivery additional requirements for steel castings, nor BSEN 10340, which we spoke about before, which defines structural alloys for cast steel grades. They do not recommend NDE or NDT protocol. Instead, they say that the casting should be subjected to non-destructive examinations under conditions agreed at the time of inquiry and order. So this would be an agreement between the manufacturer, the casting designer supplier, and the customer. In this case would be the steelwork contractor. There is some language in BSEN 1090 Part 2, Execution of Steel Structures, Section 5.4 includes requirements, and I think you have to be careful about calling it a requirement because it actually says unless otherwise specified. So it's important to interpret that what it is saying is unless that otherwise specified. It is not telling you that these testing and acceptance criteria are appropriate for your project. So it's important to read that carefully. Consider that the choice of the inspection method, the extent of the part that is inspected, the acceptance criteria that is set, needs to be based on evaluation of the part geometry, as well as the stress distribution under anticipated service conditions. So over specification, which is the second question here, the most stringent NDE protocol will inflate the cost unnecessarily, whereas under specification could, or the specification of the wrong type of NDT or NDE perhaps, could lead to performance issues. So it's important to have someone with experience with both the the standards, the processes, and how they correlate to structural performance involved in the project. So this is an image of a technician proceeding with production welding. So you can see on the left here, he has gouged out some locations that did not meet acceptance criteria. They're then replaced with a WPS that will meet the parent material criteria, and again, re-examined with all of the types of NDE that were done before. And then the last step again is the final heat treatment to relieve residual stresses. So now that we have a quality piece of metal, the machining post-processing commences so that we can be sure that these elements will fit up in the field. So they're machining bolt holes in here. You can see the finished element. So this is a CNC file that will match the flange plate of the product, or of the attaching member flange plate and bolt holes. We've incorporated in these sort of construction aids, these clocking marks, these flat ends here that help them know in the field or in the shop that things are in the right place, because the castings actually they're not symmetrical, so they do have a right way up. And to prove that out, we also put an up arrow on them, which might seem cheeky, but really if you're lifting like 11,000 pounds of steel in the air, it's reassuring to know that it's the right way up before you get it up there. So here you can see many of the castings in the awaiting coating before going on to the site. And it's always wonderful to see your erection team have this reaction to the first time that they set about to erect the first latitude of these castings. All right, a few FAQs. I'm not sure we have too much time for these, but these were, maybe we can see if we have any questions. And as those questions come in, I can maybe talk about surface finishing coatings, but otherwise I'd like to take your questions and essentially just remind you that there are other case studies in the guide, Appendix A. Be sure to visit that. And other than that, we can take questions. And yeah, as I said,
Thank you. Yeah. Thank you, Jennifer. That was great. I love the videos. I always learn something new when I hear you present, and indeed we have some questions. You've answered a lot with your presentation, but I'm going to pick up a couple of them. And the first one is related to the AESS, which is a metric system used mainly in the States for defining surface finish, architecturally exposed stainless steel scale. And the question is, can steel casting achieve all levels of AESS? It comes in 5 levels, but I think Jennifer will explain.
Yeah. Absolutely. So there are categories, and then there's a custom category, which is the 5th. It's important to understand that AESS specifications are describing the level of fabrication craftsmanship. So it is describing the appearance of welds, it's describing the alignment of bolts. Castings are the part or a piece, right, that will then be welded to the incoming wrought steel. So that weld is what is being discussed in the AESS standards. So whether it's a weld that's between two wrought steel members or between a casting and a wrought steel member, the remediation requirements are going to be the same for the weld. One consideration that is actually germane to one of the slides that I had here, with wrought steel, there is a standard sort of surface finish, and we understand we blast it and we coat it, and then there's typically a conversation about, you know, what is the coating system going to look like? Again, reminder, that's not covered in the AESS specification. It's all about fabrication craftsmanship, so coatings would be separate. But with castings, we have a different opportunity in that we can actually control the surface finish. So initially, as cast, there it is, castings have sort of a mottled surface texture because they're cast against sand. There are standards, ASTM and Strata standards that talk about surface finish, so grinding and blasting and whatnot that would need to be done to upgrade. And that will mean that we can upgrade it so that it matches the attaching wrought steel, so that when the whole thing is coated, it looks similar. It also gives us opportunities in this image that you see on the slide. There was actually a decision made by the designers that they wanted to kind of see some of these imperfections. So they wanted to be able to tell that this was a casting. Had they specified that they wanted it to be completely smooth, there would have been a different process to make it look smoother. There's an article that my colleague Jacinda Collins and I wrote in Modern Steel Construction and also Structure that talk about considerations for like steel castings and other stainless and things that weren't necessarily included in the first AESS specifications. That helps to talk about how those categories can be applied to steel castings. Also, what they're doing is they're replacing a whole bunch of labor and fabrication craftsmanship effort that would be needed to create a weldment that would be of similar quality to the casting. So I think my answer is they can achieve even higher AESS than wrought steel.
Indeed, thank you. Now we have a question saying, are castings available in weathering steel?
We do not have any standardized weathering steel products, but there are cast steel grades in that would have similar corrosion properties to weathering steel. So in both ASTM and EN, they're not kind of nicely designated with a W for you, but speaking with a metallurgist, we could, there are certainly equivalent grades, I think, too, in the same way, similar way, fashion that we have like duplex and super duplex equivalent stainless steel cast grades.
Right, yeah, true. Now, there's a question about designing how you connect the casting to adjacent wrought steel elements. For example, how would you design the threads?
The threads, if you had a threaded cast part,
I'm not quite sure. Let's wait for that person to clarify exactly what is meant, because we've got a couple of questions above it I see now on the welded joints. Shall we look at those quickly? Sure. So we've got a question about temporary works, and the question is, in the slides for welded joints, temporary external fitting brackets were used. So these are external, and the question was, can you use internal sleeves or spigots?
Yeah, absolutely. We have, so the welded joint is coordinated with the steelwork contractor. So in some applications, we'll have sort of a beveled nozzle line that fits into, say, if it's a tubular structure, which gives them sort of a backer. In other applications, the weld joint type that they really wanted more of like a detailed backer, or they put their own backer in. Those tabs, I think that you saw, yeah, those were like the temporary kind of tack weld elements to put everything into place so they could execute the weld. Let's see. We do, so in the foundry, they have to move the casting around. So each heavy casting has a lifting lug or a few of them inside in different locations. We coordinate that with the foundry. So how are they planning to move this thing around? Are they going to wrap a chain around the outside, or do they want to lift it from the inside? So those are things that could also be either casting and incorporated, or you know, if it's at the discretion of the erector, the tabs can be welded when they receive the part.
Thank you. I think we have generally answered most of the questions. Some of the questions were asked before we spoke about, like the question on embodied carbon, and you can refer back to the publication. And I'd also like to remind you that the publication is available from SCI Shop, but it's free of charge. So as I mentioned, this is the last of the 19 webinars we have run in 2025, and only 5 of them actually are free to all. Most of them are only available to SCI members, so you know, maybe you should think about becoming an SCI member if you want to access more webinars like this. So we have got not only webinars, but we've got courses coming up, steel connections, composite construction, and then me doing the high strength steel course in March, plate girder design. And yes, something for everyone. There's piling. There's a webinar on bridges, I think, coming up. So I think that's all for today. A big thank you to Jennifer for that wonderfully visual presentation. And thank you to everyone who joined us. And great, we'll see you next year at some more webinars. Okay, that's goodbye from us then.
Thank you.